Good morning. Welcome to another day of virtual notes. Again, we're hoping that we are back in person tomorrow. If we are in person tomorrow, we will be taking your chapter 4A test at that point. But for today, we're going to continue on into looking at our graphs of sines and cosines. So just as a quick review, remember that we have both cosine and sine graphs. Both were like this wave-like um, picture graph, but they were slightly different. So our sine graph starts at 0. We have another intercept at pi, and our last intercept is at 2 pi. Whereas our cosine graph starts up at 1, we're down at -1 at pi, and then back up to that 1 value at 2 pi. And we also call these periodic because they repeat themselves over a specific period of time. We said that for both of these graphs that period was 2 pi. So notice that for our sine graph, I started at 0 and halfway we are back to 0, but notice that we have only covered the positive values. So we have not completed a full cycle because we have to go through those negative values as well. So we have to go the complete 2 pi. Now, our cosine graph looks slightly different, but the period was still 2 pi. So I'm starting at 1 this time. And notice that it takes a full, again, 2 pi for us to get back to that 1 value. Today we're going to be looking at another new term, which is called our amplitude. So amplitude is going to be half the distance between the maximum and the minimum. So notice that our maximum here is 1 for our sine graph, and our minimum is -1. And even as it repeats itself going in both directions, because it's periodic, it repeats those same values over and over again, which means that I don't ever get above 1, and I don't ever get below -1. So our amplitude is we're looking at half the distance. So I can take my maximum, which is 1. We're going to subtract -1 because that would be the distance. And so I get 2. And then if I want half of that, I would divide by 2. So 2 divided by 2 gives us 1. So for our amplitude for sine, we do get 1. Or in other words, we can kind of think about this how high or what is the distance from the x-axis. So notice that we go up 1, and that gets us to our maximum, and then we also go down 1. So our distance from the x-axis is 1 in both directions, and that is what's represented by our amplitude. For our cosine graph, it's going to work very, very similarly. So notice that since my maximum is still at 1, my minimum is still at -1. If I find the distance between those, 1 minus a -1 gives us 2, divided by 2 still gives us 1. Or in other words, we are 1 unit above and 1 unit below. So that is the distance or height from my x-axis. So just kind of thinking about trying to put some of this stuff that we have talked about for sine and cosine. So just some of our basic characteristics. So notice you're going to fill these in as I fill them in on mine. Our domains, remember domain is what our x values are. So our x values are going to be what we're allowed to plug into our function. And for sine and cosine, we are allowed to plug basically anything in. And so we can go from -infinity. Now, we do need to recall that these things that we are plugging in are going to be angles. So we can plug in any number that we want. But because, again, remember that sine and cosine are relating angles, my input are angles to my output, which are numbers. Now, we did just look at, so going back to these two graphs, So my inputs or my x values can be anything. However, if we look at both of these graphs, notice that our outputs or our y values cannot be anything because we do not go higher than 1 or lower than -1 on either one of our graphs, which means that our range is restricted. So we can be 1 and -1, so it's going to get a hard bracket, but our range is -1 to 1 for both sine and cosine. Again, like last time, we talked about that our period is 2 pi. We've now talked about that our amplitude is 1 for both of these graphs. And then the last one is a little bit different because notice, remember, for our sine at our y-axis, we are looking at 0, 0. We're starting at an x-intercept, whereas for cosine, remember that we are starting up at 1. So they have different y-intercepts. Again, they're similar in a lot of ways, but we do need to make sure that we're picking up on a couple of the key differences. So remember, as we said, that these are going to be our two parent graphs. So those are the graphs that we get when we've done no other transformations to our graphs. However, we can transform these graphs. So multiply, divide, add, subtract things to these graphs, just like we have with all of our other graphs. Today, we're specifically going to look at what happens when we multiply by things, both on the outside and on the inside. So in order to kind of figure out what that looks like, we're going to look at some Desmos graphs. So here I have both our sine graph and our cosine graph. So this is my parent function right now, this red function of my sine graph. So let's look at what happens if I multiply by 2 on the front side. So notice that normally we go through 0, 0, which we still do for our blue graph. For our normal parent function, our maximum is at pi over 2 comma 1. Now for our blue graph, our x value for our maximum is still at pi over 2, but now we're at 2. Likewise, we can also kind of see now that our minimum over here is now at 3 pi over 2 -1 for my parent function. And now we're at -2 for my stretched function. So notice that this has been stretched away from our x-axis. So it's become taller. I haven't changed any of my x values. So all of my x stuff still stays the same. But I have changed the distance that we are away from our x-axis. And again, remember we called that the amplitude. So that value in front is going to affect the amplitude, or basically how tall and how low our graph goes. This is going to work similarly with our cosine graph. So this is my cosine graph. Again, we're up at 1 and down at -1. So now when I multiply by a number, notice again, I have a very similar shape. So I still have a maximum at 0, but now my maximum is at 3, which makes sense because again, that's the value that I multiplied at the front. Likewise, I still have a minimum at pi, but now my minimum is at -3. So basically that value is going to become our amplitude. Now, if we happen to multiply by a negative, hopefully we recall from when we did our transformations before that that is going to reflect our graph vertically. So normally our red graph is our parent graph. So normally we go up first and then down. Whereas now we're going down first because we have basically flipped this red graph across my x-axis. The same is true for our cosine. So notice that our cosine has been reflected. So this is our reflection. Normally we start up at a maximum for our parent graph, but for our reflected graph, we're going to start down at a minimum. We looked at whole numbers on the front, but we can also look at when we have fractions. So notice that instead of stretching it this time, remember we call this a compression. So now my maximum is at 0.5 or 1/2, and my minimum is at negative 0.5. Same thing if I had 1/3 for my cosine. I have a max and a min at positive and negative 1/3. So whatever that value in the front is, that a value, that's just going to be our maximum and our minimum. So we can kind of look at this. So as my a value gets bigger, we're going to keep getting bigger. And as our a value gets smaller than 1, but closer to 0, we're going to get smaller and smaller and smaller. If I flip it to negative, it's going to reflect it. The more negative we get, it's going to get taller again. And then the same thing is going to be true for our cosine graph. So we can come back to our notes here, and we can delete this box. And we can say that again, this a value is going to vertically stretch or vertically shrink. Basically, the absolute value of a is what our amplitude is. Also over here, we can note that if a is less than 0, there will be a vertical reflection. Now, let's look at what happens with this b value. So for our b value, again, I'm starting with my parent functions. So this time, let's look at here's my parent graph of sine. I'm multiplying by a 2 again, but I'm multiplying it on the inside of our function. And so notice that I still have a similar shape, right? I'm still having this like curved wave-like function, but notice that my waves are happening at an increased frequency. So they've kind of been squashed towards my y-axis. If I look at my cosine graph instead, we can see this time I'm multiplying by a 4. Now my frequencies are even shorter. I'm getting even more like curves within the same amount of distance. Remember that our normal distance that it takes to create one full curve, or in other words, to go from the start to the finish of one cycle is 2 pi. So let's see when we're on this other graph, right? I'm starting at a maximum. My full cycle is when it takes me back to get to another maximum. So notice that we're at pi over 2. Okay, well, let's go back and look. When my sine graph, again, all the way back for a full cycle is 2 pi. When we had our sine of 2x, now this time I'm just at pi. Okay, well, what happens if I divide instead or multiply by a fraction? So notice that this time our frequency gets longer, or in other words, it's going to take me a greater distance to get to my full cycle. So notice that we have doubled our distance. Even though I divided by 2, I doubled my distance. Whereas when I multiplied by 2, I halved my distance. So what we see here is that we have a reciprocal or an opposite relationship. So when we divide by 4 here instead, it's actually going to take us all the way out until 8 pi to complete one full cycle. So we're going to call this our b value, okay, because that's what we're labeling this here. If b is a whole number, it's going to make our period shorter because we're dividing, versus if b is a fraction, it's actually going to make our period longer because we're dividing by a fraction, which is the same as multiplying by a whole number. And let's look at what we mean by that. So let's do some examples together. So on this first one, I have y equals 3 times sine of x divided by 2. So we're going to look at my amplitude. So again, remember my amplitude is just going to be whatever that front number is. So we can easily just say So we can just say that that's 3. For our period, so again, remember that it's this 2 pi divided by whatever our b value is. But notice that our b value here is technically a 1/2, not a 2. So I have 2 pi divided by 1/2. So again, dividing by a fraction is the same as multiplying by the opposite. So I'm multiplying by 2. So we get a 4 pi. So going back to our slides, I'm going to type in 4 pi. Looking at our next one, something to be careful about is notice that, remember that our amplitude is the absolute value of that front number. So even though we have a negative there, it's the absolute value of it, so I still get 2. Now, for our period, remember that our formula is 2 pi divided by our b value. So in this case, that's going to be 2 pi divided by, notice that our b value here is 2. And so if I take 2 pi divided by 2, I'm just going to get pi. And so that would be our answer. Then on our next one, again, notice that I can have fractions in front, so that's fine. So our amplitude this time is going to be that number in front, which is 1/2. And since I don't have a b value this time, my period is still just 2 pi. So let's go from a graph maybe now instead of from an equation. So notice that we have a little bit of a different graph here because I'm not starting at a 0 or up at a maximum, which is fine. We'll look at other shifts and things like that later on. But notice that instead of my maximum being at 1, our maximum is now at 2. Instead of our minimum being at -1, our minimum is still at -2. So we know that for the amplitude of this graph, it had to be 2. We're not going to worry about this phase shift. We're just going to look at the amplitude in the period. So again, remember the period is how long it takes for us to get through one full cycle. So we are starting at a -pi/2. And so that's our 0. So we go through all of our negative values and we're back to pi/2. So the distance between -pi/2 to 0, remember I'm talking about a distance for my period. So the distance that it takes me to get from -pi/2 to 0 is still pi/2. Then to get to pi/2 again is going to be pi. But I've only completed the negative portion of my values. So we still have to go through all of these positive values. And that takes us all the way to 3 pi/2. And notice that if I needed to figure out what the distance between 3 pi/2 and pi/2 is, I can always subtract. So 3 pi/2 minus pi/2 gives us 2 pi/2 or pi. So we said that this first chunk of our negative values, it took me pi/2 to get to 0, then another pi/2, so this distance is pi. And then we also said that our distance then to get to 3 pi/2 was another pi. So overall, our period here, even though I've shifted it backwards, is still 2 pi. It still takes us a full 2 pi to get that full range of values that we need. Again, if you have any questions, please feel free to leave me here them for me here, and you will submit your completed slides on Google Classroom. I have also posted your homework assignment for this lesson as well.